So we'll have today one very interesting topic, which is in front of you. Correlation plus I have marked because other than correlation also, some related definitions we'll be studying today. And regression will be taking up in the next class, maybe tomorrow, same time.
Sure, sir.
So one thing, guys, why I have taken up this topic is that myself, during various interviews, when you go for data science interviews or those kind of interviews, so people will test your basic statistics first. So what generally everybody's favorite question, even if they don't know, they will ask, what is the difference between correlation and covariance? Correlation and covariance, what is the difference? At least 3 or 4 times I am caught on this question. So I thought I'll make a complete lecture for this so that nobody else is confused. Okay. So we'll devote complete 1 hour today for this question. What is the difference between covariance and correlation? Okay, so that is the topic for today. So these are the things we'll be studying. Just you can have a look. I'm not reading them. So a lot of things we'll be studying. You see, on the left-hand side, we'll finish today from point 1 to point 11. And 3 points on the right-hand side we'll take on next lecture, regression. So all this will finish today. The number of topics are large, but everything is very correlated. Okay. So let us start one by one. So what is variance? So variance, I think we already know by this time because 3-4 times we have repeated in previous lectures. There is suppose there is a data column called height of adults. So what is basically height of adults means it is containing, say, 150 adult heights more than 80 years. More than 18 years. Everybody is above 18 years. And we are measuring heights of 150 people. So we'll have 150 entries in the data set. That data column will have 150 entries starting from 0 till 149. Start from our index always starts from 0 and ends with 1 less. So 149. 0 to 149, total 150 heights of adult people above 18 years. Like that we have different entries are there. Now I'm telling above 18 years is a very big range, right? People easily live up to 80 these days. Maybe 90 and above 90 is rare. But 70, 80 is very common nowadays. If somebody dies at 65, 67, people call it that is died early. That's because of all medical facilities, right? Medical facilities and all that progress in science. So from 18 years till 85 years is a very big range of people, and height can be different from different people. Myself, I have seen the tallest person, I have seen 6 foot 4 inch. That's what the tallest person I have seen from my eyes. And like everybody of us goes to some kind of circus and all. So some jokers and all will see those are fully adult people, but height will not be more than 4 feet, 4.5 feet. Okay. So from 4 feet to 4.5 feet till tallest man stays in Pakistan. His height is 7 feet 9 inches approximately. 7 feet 9 inches is his height. And the smallest person which you and me have seen is 4 feet, half of that. So it's a very big range, right? So we know smallest number is 4.5 feet and highest number is around 8 feet in Pakistan. We have our tallest person. So what is the range? 8 minus 4.5. 8 minus 4.5 means 3.5 feet is the range of our data because smallest is 4.5 feet, highest is 8 feet. So 8 minus 4.5, 3.5 feet is our range. But range is a very crude kind of measurement for this. There is dispersion, right? Dispersion, how much spread is there in the data? So data is spread from 4.5 inches till 8 feet, 4.5 feet till 8 feet. It is spread. So range is the very simplest measure of it. Just the max minus mean is your spread. So that is a kind of very crude and it doesn't tell much. So we have better measures. We name them variance and standard deviation. So even if you have forgotten, at least some piece of that you might be remembering. So variance is shows us how much dispersion is there in the data, how much your data is spread from the mean. Mean height is suppose 4.5 is the least height, and say 8 feet is the tallest height in the world. Then mean will be some feet around 5 feet 8 inches, generally average height 5 feet and 8 inch. I am 5 feet 8 inch, so I have average height. Okay, so I am average height person. So average is around 5 feet. So mean is the 5.8, and around the mean, how much spread is there of the data? How much below the mean and how much above the mean? That kind of spread when we talk about. So we have two nice, beautiful, very useful kind of statistical measure. We call them variance and standard deviation. We'll see their formulas also later on. So why I'm telling this is, this variance belongs to only single parameter, single variable. Variance, we measure for a single variable. So we had a height of the people as was the variable, and it was containing 150 entries. So within that we are measuring our variance, standard deviation, range. So it is for a single variable. But I will show you one example here. See here, one example I will show you. Here. Right. See here, this graph on the right hand side. On the left hand side, it is a tabular data for a small retail store, a grocery store or a retail store. So generally temperatures which are given here generally are belong to a colder country. So our temperatures are, our higher temperature is 44 degree, 45 degree, and Nagpur and all, it is even 48, 49 degrees sometimes. Okay, in Rajasthan, it is 55 degrees in the desert. Okay, but they are not, this data may be belonging to a colder country. Some, maybe let us say United States, it's a colder country, right? So can somebody tells seeing the data, somebody tell me what is the lowest and highest value in this table of temperature? Lowest and highest value of the temperature, guys, in this table?
11.9 is the lowest.
And highest?
25.1.
25. Yes, correct. So there is a range. There is a range, right? 11.9, you need a sweater, nice sweater, because it's cold. And 25.1 is hot. Little bit small woolen. Not woolen is not required. Simply some small cotton shirt is okay. So there is a range. So for this range, we can always have range, minimum minus maximum. We can measure variance. We can measure standard deviation. So that is not the topic right now I want to talk about. So right now here we see there are two variables. One variable is temperature. In that some range is there. And another variable you can see on the right hand side column, which is ice cream sales. For that store, ice cream sales is given in dollars. So there are two variables here. One is temperature and one is ice cream sales. So now, even if little common sense will tell you that ice cream sale on 25.1 degree will be higher than what we see on 11.9 degree. 11.9 degree, very few people will buy ice cream. But 25.1, many people will buy. And suppose we are talking about India 44 degrees, everybody will buy ice cream and cold drinks, right? Some kind of cold drinks. So we can say that when temperature rises, ice cream sale also rises. It's a very common sense, right? So you see the graph. Graph is also similar. Temperature is plotted on the x-axis and sales is plotted on the y-axis. See, you can see the rise. Temperature is increasing from 10 degree to 26 degree, and ice cream sales in dollars are increasing from $100 or $0 till $700. Okay, so that is daily sale. Daily sale. For daily selling for a small grocery store, $700 ice cream daily sale is not bad. For a small store, bigger store it is nothing. So I meant to say there are two variables here. One is temperature and one is sales. So when we study one single variable, when we study the variable with a variation within a single variable like temperature separately and ice cream sales separately, when we study them separate, then variance is applicable or standard deviation is applicable. Standard deviation is nothing but square root of variance, right? Both are kind of formulas are similar. Just take the square root of variance, you will get standard deviation. So you can say that both are similar units because very simply related. When you take a square root of variance, you will get standard deviation. So when we study temperature variable separately and ice cream sale variable separately, then you have variance in picture. But what if I have to study both the variable together? For a grocery store, how temperature varies is of no importance. For a grocery store, how temperature is varying across the year is not important. It is more important for a weather scientist, or it is more important for a airport. Though for those people, how temperature is varying, that is important. For a grocery guy is not bothered. What he is bothered with? When temperature is rising, how my sales varies along with that. Ice cream sales. So he wants his ice cream sales to be maximum. So what is the relationship between rising temperature and sales of the ice cream? That's what he is more interested. So what if we have to study two variables separately, two variables together? One thing is increasing, so how other thing is increasing or decreasing? So in that case, we have something called covariance. So now here I have told you the difference between two quantities, variance and covariance. So variance is nothing but studying range in a single variable, and covariance is nothing but together we are studying two variables, generally linear. So generally two variables when we are studying, that time we have covariance in picture. So how with variation of one variable, other variable is moving, like my temperature is increasing. So how my sale is increasing? Okay, is it increasing very fast or it is increasing but slope is very less? Those kind of things I'm interested. And third thing is correlation. Correlation is something which I would explain you later. First, let us study variance and covariance. Correlation is also something very related to correlation is very related to covariance, but I'll tell you little later. Okay, now this variance formula, we have done some numerical also on it. Ice cream sales, like take the temperature. So there are 15 entries in the temperature table. Take each one of variable and deduct mean of that particular table, particular ice cream temperature. You take the mean and deduct from every entry of that table. Take the square root, then sum everything and divide by the total number of entries, like 15, divide by 15. If 15 are the entries. Formula, if it is a population, you divide by n, and if it is for a sample, then you divide by n minus 1. Why it is so? We are not going into depth. That is something which will be studied by the guys who are doing MSc in statistics. Right now, we are studying applied statistics. So we should know when we deal with population data, to calculate the variance, we have to divide by n, the total number of entries in the table or that column. And when we are dealing with sample, then we are dealing with n minus 1. When population mean is unknown. So when population mean is known, then you divide by total number of total number of entries, and when population mean is unknown, then you divide by n minus 1 entries. Similarly, if we are dealing with population data, you divide by n, and if we are dealing with sample data, you divide by n minus 1. That is the formula we have to remember. And how it is to be calculated? We have done it it is very simple to calculate variance. If variance is more, means spread is more. So this is what we have studied in the previous lecture. So I will not repeat it. So what variance shows? Suppose variance is 0. Variance is 0 means, suppose table has 150 entries of height. So all height are equal. So all heights are 5.8. First record is 5.8 inch, second record 5.8 inch, third record 5.8 inch. All the records are 5.8 inch. There is no variation in height. Then variance will be 0. But if one is very small and one is very big, and in between, there are numbers in between, then variance will be large. So if variance is large, means our spread is more. If variance is 0, means there is no spread. If suppose for a data variable, if variance is 0, that means that data column should be deleted. That data column is of no value to us. All the entries are same. So such a data column is not useful in machine learning applications. We want, for a machine learning algorithm to work properly, we want at least some variance. And if variance is more, the learning by machine learning algorithm will be more. Like that. So like if we want some variance in the data, constant data, if some field is constant, you better delete that column from the data set. It has no value from machine learning point of view. Okay. So now we are dealing here. So first, if population mean is known, you have to divide by n, total population. And if population mean is unknown, you have to divide by n minus 1. Now these two formulas, can somebody tell me what is expected value? We have studied it. Does anybody remember what is expected value? What is expected value of a, suppose data column? There are only 3 entries, 10, 20, and 40. One entry is 10, second entry is 20, and third entry is 40. What is the expected value of this data column? Okay, what is the mean of this data column? 10, 20, and 40. What is the mean? 10, 20, and 40. What is the mean? Sarthak?
Sir, 70 divided by 3.
You have to tell, what is the value? 70 divided by 3, how much?
Sir, approximately 20 point 23
20 point something. So expected value is another name given to mean. Okay, expected value is, there are some other formulas also to calculate expected mean, but in very layman's term, expected mean and expected value and mean are same. Okay, in a very layman's term. There are some different formulas to calculate expected value, but I'm not going into detail right now. And if you like, I would like you to do some research today and educate yourself on what is expected value and how is it calculated. For a layman's person, layman's language, expected value and mean are same. But there are some different formulas, different ways to calculate it, and there are some different meanings to it, expected value. So I want today all of you guys to Google search little bit Google search and find out what is expected value, how it is calculated, and what are its uses. You write down what is expected value, how is it calculated, and what are its business applications. So these 3 things you should educate yourself about. So variance, one formula for variance is this given on the top. I'm not going into detail of this formula. Expected value of x square minus expected value of x whole square. So this is nothing but the variance of x. So I'm not going into much. Don't worry if you don't understand this formula. Let us not go into detail. But only thing is variance. If you can see the formula properly, if you see the formula properly. Just a second, my mouse is not working. If you see the formula properly, then you will see that it is always square involved in that variance formula. X, value of x, xi minus mu, mean. So square is involved. So square can never be negative. Square will be either 0 or square will be some positive number. So your variance and standard deviation can be 0, but it can never be negative. It will be a positive number or it will be 0. Okay. So your variance x means variance of x will be a number always greater than equal to 0. That is the thing to be remembered. So we go now. Let little bit. You will remember the formulas. You may not remember, but these things you will always remember. That's why I'm showing you graph. See here. This formula, like one is left hand side is low variance. How it is looking? Kind of straight line. Kind of straight line it is looking, right? See here 0 in the middle. It's a mean line. Mean. So it's a mean line. 0 is nothing but your mean line. Around the mean line, it is scattered data very up and down, very nearby, it is scattered. Minus also going a little bit and plus also little bit. So it is very low variance. Now your right hand side, you see the mean line. Height is it is going much above and much below also. So variance is more. So seeing the graph itself, if you don't want to calculate the variance value and find out whether there is any variance in the data, just plot it. There are many Python code available. In one line of Python code, you can plot the variance of a data field or a data variable. So if graph is coming like this, very near to mean, that means variance is low. And if graph is coming too much scattered around the mean, then the variance is high. Only thing to remember, it will tell you whether variance is low or high. You cannot find out the number. How much is the value of variance? If you want to find out value of variance, that means you have to apply this formula. This formula you have to apply, and if you go, like I will share the lectures with you, PPTs are already shared. So if you take a little bit pen, you will find out that this kind of numerical we have done in the class, how to calculate the value of variance. Okay, guys. So now we'll come to, this is variance. So variance is all about variations in single variable. Now we are talking about two variables. How, with temperature, ice cream sales varies. Ice cream sale is increasing with temperature. So what is the relationship between rise in temperature and variation in ice cream sale? That is the kind of thing we want to study. So there are two variables involved, x and y. So now you remember here, see here, variance formula, x minus mean whole square. X minus mean whole square was there. So it is also very, remember this formula, x minus y whole square is not there. So x minus mean into y minus mean divided by n. So here also is a squared, right? It's a squared. X into y degree 2. So here instead of square, you have x minus mu into y minus mu. You take the sigma, divide by n. If population mean is known, means we are working with population. And if population mean is unknown, then x minus x bar divided by x bar is nothing but your sample mean. X bar is your sample mean. So x minus x bar into y minus y bar divided by n minus 1. So here also you see same formula. Here it was squared, n minus 1. But here instead of square, you have another quantity y. Why? Because covariance always studies the variation with two variables. So you have x minus mean into y minus mean. Take the summation over all the number of entries, divided by n or divided by n minus 1. So we'll do a numerical related to covariance. So things will be more clear to you. So Give me a second, guys. Yeah. So this we have seen. Now this formula also. Now covariance, I told you covariance can be a covariance. Variance can vary between 0 and positive infinity. Variance can be either 0 and it can go up to infinity, positive number. Covariance is also, but covariance can go negative. Why covariance can go negative? Because if mean is greater than any x entry, this entry will become negative. If mean is greater than any y entry, this difference will become negative. So this can go negative. So covariance goes from minus infinity to plus infinity. Covariance can vary between minus infinity to plus infinity. Reason is in front of you. See here in this formula, if x minus mu, suppose x minus x is greater than mu, means it will be x minus mu will be positive. And y minus mu, suppose y is less than mu, this will become negative. If this becomes negative, and overall there are lot many negative entries like that. If you sum up everything, the covariance will go negative. And suppose you are measuring ice cream sales in rupees and temperature in degree centigrade. Remember, now listen to me. Ice cream sale I am measuring in Indian rupees and temperature I am measuring in centigrade. That is one thing. Now I am talking about US. US people don't use centigrade. They use Fahrenheit. Generally, people in US, they won't use centigrade. Their unit of temperature they use, more popular unit is Fahrenheit. So their ice cream sale will be in dollars and temperature will be in Fahrenheit. For India, the ice cream sale will be in rupees and temperature will be in degree centigrade. So in both the cases, units are different. Units are different means scales are different. So in that case, both the cases, the covariance value will be for exactly same curve. If curve shape is same, but still, if your units are different or your scale is different, covariance also will be different. Means for India, you are measuring in INR, sales in INR and temperature in degree centigrade. For US, you are measuring y-axis sales in dollar and y-axis in dollar and x-axis in Fahrenheit. Scales are different, right? Scales are different. So value of, even if curve is same, the value of variance in both the cases will be different. So covariance is scale dependent. That is what to be remembered. Covariance is very much scale dependent. If scale varies or unit varies, then your covariance value also will be varied. So it is a difficult unit here. Suppose I am measuring my sale in 1,000 rupees. 1,000 like I measure my scale in 1,000 rupees, and x-axis is in centigrade. That is okay. X-axis I am not changing. Y-axis, first I plot with my sale I plot in units of 1,000 rupees. Then second time what I do? X-axis same, centigrade only, but y-axis instead of plotting in 1,000 rupees, I plot in lakh of rupees. That lakh, whatever the quantity in 1,000, I convert into lakhs. I divide by some zeros. I divide by some zeros. Same thing I'll put. Number is same. But first time I plotted in thousands, and then same thing I divided into lakhs, units of lakhs, and plotted on y-axis. Number is same, like quantity is same. I am measuring same 1,000 rupees. In one time I am telling is 1,000 rupees. And second time I am dividing it by like 100,000, making it lakhs. So it is 0.01. So it is 0.01 lakhs, right? So second time I am telling in 0.01 lakhs and first time I am telling in 1,000. Both are same. So first graph I am plotting with thousands of units, thousands. Second plot I am converting same number into lakhs and plotting. In both the cases, the value of covariance will be different. Why different? Because units are different, scale is different. And if you see the formulas, you will very easily understand by looking at the nature of formulas that if here my scale will vary, my products also will be varying, and the overall covariance result will be different. So it's a not that useful thing, na? Because I'm plotting two things, same thing. One time I'm calling it in thousands, and second time I'm calling it in lakhs, same amount. But my unit of covariance is different. Then how will I say which is more covariance and which is more less covariance? Which covariance is more and which covariance is less? I cannot say, na? Because just by varying the unit, my covariance is varying. So I need some better unit. I need some better unit. If I see the unit, I should be able to tell whether variation is more or less, spread is more or less, variation is more or less. That I should be able to say just by looking at the number. But here, covariance number is not telling me anything, because if I vary the unit, then covariance number also varies. So if there is a large covariance, I cannot say that variation is large, because units, somebody might have measured instead of meter, some height instead of measuring in meters, somebody might have used the millimeter unit. So my covariance number will come very large. So I need some more reliable unit. Okay, so now two things we have learned so far. Variance, whenever we measure, it is a spread for one single variable. Covariance is about two variables. If I vary one variable, how the other will vary. Okay, so that is all about covariance. So unlike variance, covariance is calculated between two different variables. Got it? Its purpose is to find value that indicates how these variables are vary together. Means the magnitude, like covariance minus infinity to plus infinity. It is supposed to tell me what, like variance, like variation is more or less. But I told you one thing. If I vary the unit, covariance value also will vary. So I'm not very happy with this covariance unit. So I need a better unit. So we'll do that with correlation. Okay. So now I have plotted here a couple of more graphs so that you understand what kind of positive correlation. Positive covariance means I'm varying x I'm increasing, y is also increasing. See, it's an increasing straight line. Negative covariance means x I am increasing, y is decreasing. It is negative covariance. And it is randomly distributed. The circle it is making a randomly distributed. So it is zero covariance. So you should be able to interpret the graphs like this. So if it is a positive, x increases, y also increases. That is positive covariance. If it is reverse, x increases, y decreases, then it is negative covariance. And if there is no covariance, just some random shape will be there. Some random shape will be there, like circle or some randomly they will all be distributed all around. There will not be any pattern. Then it will be zero covariance. That is one thing. One more, one more plot I have seen just for your understanding. See, it's a perfect straight line on the left hand side. There are three plots, right? So see the leftmost, it's a negative covariance, but it's a perfect straight line. It's a perfect straight line. So there is a very strong negative covariance. There is a very strong negative covariance, very large negative covariance. Middle plot, if you see, just scattered like that, there is zero covariance, no pattern, no relationship. If I vary x, y is not varying at all, just random. So it is zero covariance. Now it is perfect straight line here. On the third one, it is perfectly increasing. So perfectly increasing means if your straight line is perfectly increasing, it's a very large positive covariance. If your straight line is perfectly decreasing, then it's a strong negative covariance. And if there is a random distribution, there is zero covariance. Now, after seeing this graphs, you should be able to tell at least the variance is positive or it's negative or there is no covariance. And you should be able to tell approximately if it is a large covariance or it's a small covariance just by looking at the plot. So have a look here. See here on the left hand side, I say positive covariance, but it's not very strong positive covariance. Why? It's not a perfect straight line. It is increasing, but it is slightly curvilinear. You can see it's a slightly curvilinear shape. Okay, so it's not a perfect positive. So it's not a large positive covariance. Now negative also. Negative also is also not a perfect straight line down coming. It is not coming down, it is between in the second one, in middle one, so it is coming down, but it is not very straight. It is little bit scattered here and there. Shape is also a little different than straight line. So you can say it's a negative covariance, but not very straight, very strong. Zero covariance anyway, you can find out now. But here, both positive and say first and third figure, almost perfect straight line. In that case, you have to say it's a very strong positive or very strong negative covariance. If straight line is perfect, then you have to say it is a very strong correlation, covariance. Right now, we are not going into its value. So now let us see one example, very C example. So suppose again I have a, what you want to call, like there is my retail store is there. And this temperature, of course, is in Fahrenheit. It's again US data. So this temperature, whatever X you are seeing in the left-hand side table. Left-hand side table, temperature is in Fahrenheit. Centigrade, nobody can survive on, say it's 74 degrees centigrade, no one can survive on this earth, right? So it is in Fahrenheit. So 74 degree Fahrenheit is generally lower side of temperature, maybe 18 degree or something. Exact conversion, I have formula, but I cannot tell you exactly, but around 18 degree or something. 74, 97, everybody knows 97 is your body temperature. So you have an idea of 97 degree Fahrenheit. So this Fahrenheit data, climate data, Fahrenheit temperature, and then number of customers, like with one plot is one chart is one column is temperature, other column is customer, number of customers. So with what temperature, how many customers visited the shop? Okay. So maybe again, it's a kind of, you can say it's again is selling something like ice cream only. Because when temperature is 74, which is on lower side, only 7 customers came. And if temperature is more than 7 customers are coming. So you can assume that it's some kind of ice cream or those kind of things is selling. So first is temperature, other is number of customers. That 2 columns you have. So now you have to study covariance. Covariance means with if I plot temperature in increasing order on x-axis and y-axis if I plot customer on increasing order, what is the relationship? That's what I want to study. Find out the exact number I want to find out. If I plot, very easy. By plots, I can say it is low or high, but I cannot find out the number. So now what I do, first of all, learn the steps. First of all, I take the mean of x, mean of temperature. So I add up 1, 2, 3, 4, 5, 6. 6 things I add up. 97, 86, 89, 84, 94, 74. I add up, divide by 6. I get my average temperature is 87.33 degree Fahrenheit. Now mean of y. Y is what? My number of customer. So again I add 14, 11, 9, 9, 15 and 7. I add up, again divide by 6. So 65 divided by 6, I get the mean customer as mean number of customer as average number of customer as 10.83. So first of all, 2 things always we have to do. Find the average of first column, find the average of second column. Very easy. Now again 2 more easy steps you have to do. From X, there are 6 entries, right? X, you can see there are 6 entries. From every entry, you deduct this mean of X. Mean of X is 87.33, you can see, is the mean of X, 87.33. So from every entry, you deduct mean of x. You see here. Now right hand side, right? Come to the right hand side of right half of the screen. You will see x minus x bar. So 97 minus 87.33, 86 minus 87.33. From every number, he has deducted the mean. Okay, 87.33 is your mean. So why he has done like that? See here, because you study the formula. A formula is given here only. See, formula x minus x, xi minus x mean. What is xi? Xi means x1 to x6. Like that, 6 times he has done that, taken the differences. Xi minus x bar. That's why he has done x minus y. Then we have second thing we need to calculate is yi minus y bar. So right from customers, 14, 11, 9, 9, 15. From every number he has deducted 10. See, it's the second column on the right hand side of the screens table you see. From every customer number he has deducted mean. Okay, so that's what these two things are done. Now what our formula tells? Xi minus x bar into yi minus y bar. Xi minus x bar into yi minus y bar. Product I have to take, right? Product. So now here see 9.67 into 3.17. Product is 13.65. Minus 1.133 minus 1.33 into 0.17. Product is minus 0.22. Like that, all two columns he has taken corresponding product. So now I have x minus x bar into y minus y bar on the third column. Third column here in the right hand side table, third column, I have the product x minus x bar into y minus y bar. Now what I have to do? I have to do the summation. Summation means all the 6 I have to add. So first I have to do the product and then I have to add everything. So I have added up. So my number, if I add it up, 30.65 minus 0.22, minus 3.05, 6.09, 27.81, 51.85. If I add up everything, total will be 112.33. And I have to divide by n minus 1. Why I have divided by n minus 1? Because right now I am not working with complete data, I am working with a sample. So my formula here, when I have formula here, when I am working with a sample, I have to divide by n minus 1. So I have divided here by n minus 1. N is how much? N is 6. Minus 1, 6 minus 1, 5. You just calculate. So covariance XY is 22.46. Positive number. Now tell me, if I measure this temperature, instead of Fahrenheit, I put degree. If I put degree here, degree centigrade, numbers will be different. If numbers will be different, my x minus x bar for all the 6 values will be different. X minus x bar for the all 6 entries will be different. And if I take the product and do the sum, then the numerator will be different because previously it was in Fahrenheit different number. Now it is lesser number in centigrade. So my numerator will be lesser in this case. So my covariance x pi will be lesser than 22.46. Maybe it is 12, 13, something like that. So if I vary the unit or if I vary the scale, then your covariance number also will vary. So it's a simple numerical formula here, guys. So I would like to take a stop here for a minute, and if it is nothing is you see this formula. If that is not understood, we'll repeat it once more. So what do you say, guys? Is it understood?
Yes, sir.
Yes, sir.
I want one of you to repeat now the difference between covariance and variance. Who wants to repeat? Don't worry, wrong thing is not punished. Just try somebody. What is the difference between covariance and variance? Sarthak bhai?
Yes, sir. So variance is basically where we only have one variable, and
Yeah.
covariance we have two different variables.
Yeah.
And variance is not dependent on the scale. Covariance is dependent on the scale.
Variance is also scale dependent. Variance is also, see, if I measure height in centimeters, my variance number will be large. And if I same height, if I measure in meters, my same variance number will be low. Variance is also dependent on scale. Covariance also is dependent on scale. Okay. Standard deviation also dependent on scale. Got it? Good that you made a mistake. So now you will never forget. All things, whatever we have learned so far, variance, covariance, standard deviation, they are all dependent on scale. You see the formula, na? See the here variance formula you see. X minus mean. So if X unit is different, then my mean will be this mean and this X minus mu will be different. Square will be less if I measure in meters. If I measure same in millimeter or centimeter, the square will be a large number. Okay,
Got
so
it,
it will vary,
yes,
right?
Right.
So both variance and standard variance and covariance will vary depend on. So this is variance. We are seeing here variance. We are plotting a mean, and along the mean we are plotting various either it is above the mean or it is below the mean. So low variance, high variance. Now here we are plotting two variables, X and Y. So now you understand positive correlation, negative correlation, and zero correlation. So now I will explain you one more thing, correlation, and then we'll close for the day. So now I explained you, now you have understood very nicely that my covariance varies with scale. Same thing if I measure in meters, and same thing if I measure in centimeter, my covariance will be different. So I cannot, this 22.46 is a number, positive number. It tells me something, but not everything. What it tells, what does it tell? Tell me, like anybody, Amit Parikh, what do you infer by 22.46? If I say covariance between X and Y is 22.46, what is the meaning you can take out in business terms? What is the meaning? What does it tell you? What does this number tell you? If I say Amit is having 2 crores of bank balance, then everyone will leave my lecture and go behind you. And they will show you gun and take because Amit is a very moneyed man. That's how you infer, right? Money everybody understands.
Yes.
Whether it is dollar or it is rupees, everybody understands.
Yes.
But now tell me this covariance is 22.46. What does it tell you? What does it tell you? Try something. It varies with scale, okay, but it still gives you some information. What information? Sarthak, you want to tell, or Jignesh, you want to tell? It is giving you some information.
Yes.
Yeah, tell me, Jignesh.
We can say if the positive covariance, if it is a positive covariance, that means the comparative of both variables. If one variable is increased, then other will be also increase.
Perfect. So it is giving you some.
So we can say for this example.
Yeah, now if I tell you, if this variance is large or small, what can you say? Jignesh, I'm asking you, 22.46, is it a large variance or a small variance?
It's a large variance.
That is the mistake you are doing. See, this number looks large, but instead of measuring my height, ice cream sales in dollars or ice cream sales in rupees, I'm measuring my ice cream sales in paisas. Then this scale will be, then it will look large. Same thing if I measure in rupees, this will be small. So now remember, this number is telling you positive, it is a positive number. So it is telling you only it's a positive number means with X increasing, Y is also increasing. That is for sure it is telling. But it is not telling the kind of relationship. The strength of relationship, It is not telling because it is always dependent on unit.
It's dependent upon measure.
Yeah, user unit it will depend
Measurement
on.
of unit.
Yeah, so you never say it is a large, very strong relationship, very strong positive covariance or very strong, very weak covariance. You cannot say. So now for that we are introducing this one more new thing, correlation. So correlation, whatever defect we saw in variance, what was the defect? With unit it varies. We don't want that to happen. If I see the value, I should be able to tell whether it's a large covariance or it's a small covariance. But I'm not able to do that by looking at covariance value because the unit is very much dependent on scale, very much dependent on unit and scale. It is dependent. Okay, so now to overcome that kind of weakness of covariance, I have invented one more unit. It is called correlation. What is it called? Correlation. So correlation is the standardized version of covariance. Remember, correlation also tells you is about same thing. One variable varies, how other varies. That is correlation is also same thing. How x, if I vary x, how y varies. Covariance is also same thing. If x varies, how y varies. Both tell us about same thing. Both are used to measure same thing. But covariance was dependent on unit. My correlation is not dependent on unit. Something is like that. My correlation is a standardized version of covariance. It doesn't depend on unit. Scale. If you measure same thing in millimeter, if you measure same thing in centimeter, you measure same thing in meter, your covariance value always becomes same. Exactly same number. And by looking at covariance number, I can tell the strength of relationship between x and y. So now I'm not explaining you these things. Straight away we go to this thing. Okay, straight away we go to our the same ice cream example which I showed you. So now here temperature is increasing and sales is increasing. So you see it's a straight line, but it's still not a perfect straight line. Some points randomly, like it's very near to a straight line. So I expect to be a strong correlation. I expect it to be a strong covariance. Now I'm telling you the correlation value for this line is 0.9575. 0.9575 is the correlation value. Formula I'll tell you later. But just first try to interpret how to interpret the unit. First learn that. I'm telling you the correlation value for this particular relationship between temperature and sales is 0.9505, 9.75. Okay, it is not perfect one. But if I tell you same thing, if the correlation is 1, and if I tell you the same, if I tell you if I tell you the correlation is 1, that means it's a perfect straight line. So it is this kind of line. This kind of line. Third figure. Third chart here. Perfect straight line. So the correlation value will be 1. Perfect straight line. Then here I don't have perfect straight line. So I have a little less. I have a little less than this. So if my correlation value is positive, definitely it tells me if x increases, y also increases. But now number is also telling me something. If it is perfect 1, means it is a perfect, very strong correlation. Very strong covariance. If number is 1. If it is 0.3, 0.4, that means it is a weak correlation. And correlation will always vary between -1 and 1. It will not be less than -1. It will not be more than 1. So it's a standardized version of covariance. Covariance will depend on see here the covariance was how much covariance was 22.4 ways. Our correlation value will never be more than 1. and it will never be less than -1. So if it is perfect one, we have to understand it's a very strong correlation, straight line, pakka straight line. And if it is -1, we have to understand -1 means this figure, first one. It is a pakka down coming straight line. If it is +1, it is pakka upcoming up going straight line. And if it is 0, means it is something in between whatever middle center you see this plot now, center plot. So it will be like that. Now you understood. Is it making sense? Correlation is making sense to you guys? Amit?
Yes, sir.
So now do you think it is standardized? Correlation is standardized.
Yes, sir.
It is standardized, right? Because you know that it cannot be less than 1, it cannot be more than +1, it cannot be less than -1. And if it is -1, it's a pakka down coming straight line. And if it is a +1, it is a pakka upgoing straight line. Now, how much will be the correlation of these first two figures? Can you tell me all the three figures? Just by something. Somebody guess? First, second, third, tell me the correlation. Correlation coefficient. What will be the first one? Jignesh bhai.
Yeah, it's a correlation. First figure having completely positive. We can
Tell
say
me the
it's
correlation coefficient number
near to
approximately
+1.
how much the value will be. Approximate value of correlation coefficient for this.
Okay.
Tell me, wrong is okay.
Yeah, that is 0.85.
0.85 to 0.9 I
Yeah,
can accept.
0.85.
Yeah, 0.85 is I can accept. What about second one?
Yeah.
What about second one?
Minus
It's
0.8.
Yeah, Amit,
it's
you are
about
telling.
the
What
similar.
is
Minus-
second one?
Minus
Amit?
0.85.
Correct. Third one?
That's it.
0. And
Zero, yeah.
now here it is very easy, no?
Yeah.
First one is -1. Center one is 0. And third one is +1. Now you got it. So correlation is also studying the difference between, is about studying that how with X, how Y varies. That is some correlation is also same thing. But it is a standardized version of covariance. So formula is very complicated. I will not take you to the formula, but I'll still tell you. See, this is the formula. Formula is kind of, first you calculate the covariance. See the top one. You know how to calculate covariance, right? So here we have calculated covariance here. In this relationship, we have calculated covariance. So you know how to calculate covariance. So see the top formula here. See the top formula. So first of all, you calculate the covariance. It will be some big positive or big negative number. You calculate that. Then you calculate sigma x and sigma y. So what is sigma x and sigma y here, guys?
Sir, mean of X and mean of Y.
No. This mean of x and mean of y?
Standard deviation.
Sigma is always
Sorry,
standard
sir.
deviation.
Yes, yes.
See, it is written here on the right hand side. Sigma x is standard deviation of x and sigma y is standard deviation of y. So it is easy to calculate. First you plot the two columns, you tabulate, find out the mean, take out the difference, make a product, do the sum and divide by either n-1 or n. That is how we'll give you covariance. And then you calculate standard by using your Excel sheet, you calculate standard deviation of x, standard deviation of y and divide by product of that. So that will be your correlation coefficient. Easy to calculate, right? If somebody gives you number, two columns somebody gives you, within 5 minutes you should be able to calculate the correlation coefficient. Because you know how to calculate this is the way you calculate covariance. So numerator is nothing but your covariance. Denominator is nothing but sigma x. Sigma x means standard deviation for first column. Sigma y is standard deviation of second column. Do it, product of that, divide by it. That's all. So you know how to calculate covariance, correlation coefficient. So correlation coefficient is the standardized version of covariance. And now with this thing, if anybody asks you in any interview or anywhere, you should not be confused for your life that what is the difference between correlation, what is the difference between covariance, what is covariance, and what is variance. All these three things you should remember forever. Okay. And believe me, if you are going for any data interview or any data science interview, this will be the first question they will be asking you. What is the difference between covariance and correlation? So very simple. Covariance is a big number, depends on scale. If X varies, Y varies, it studies that, how X varies, Y varies, and it depends on unit. So I cannot depend on its value. Value doesn't tell me anything. So that's why I have devised one more unit called correlation, which is a standardized version. +1 means highest level of correlation, positive. -1 means highest level of negative correlation. That's it. So now only one thing I want to tell you, that if X is increasing here I want to just with this will end today. See here where I wanted to tell you here. Yeah, here temperature is increasing and ice cream sale is increasing. I think both are directly related. Right? Temperature is, people are feeling hot, so to cool themselves they are having ice cream, enjoying ice cream. So if it is more hot, more ice cream will sell. It is, we can say they are directly related. But in covariance and correlation, if X is increasing, Y is increasing. That is not always the case. That may not be cause. Increase in X may not cause increase in Y. See, example is this. Number of sunglasses sold. Ray-Ban sunglasses. So X-axis I have plotted sunglasses sold. So one shop is selling both sunglasses and ice cream. So number of sunglasses sold from 100 to 260. And ice cream sale is also increasing. So can you say both are related? See, on some very colder places in Canada and other places, sometimes sun is very bright, but temperatures are still very low. Temperatures are still low because temperature may be in -degree, -5, -10, but sun still can be very bright. And in that, if suppose there is a snow all around, it's a hilly mountain, if there is some snow all around, you cannot stand without sunglasses. You cannot, your eyes will be kind of blurred, vision will be blurred, you will not be able to, your headache will be there, lot of headache will be there. So I'm telling that temperature and sun, they are not correlated. Sun can be very bright, but temperature can be very less. So if my sunglasses selling is more, how ice cream is selling more? You cannot say they are correlated. It is just a coincidence. You cannot say that because my sunglasses sale is increasing, my ice cream sale is increasing. That is not the relationship. Now here one more relationship here. Consider one more. Poor suburbs are likely to have high pollution. Any suburbs of the city, if they are poor, statement is they are likely to have high pollution. So what can be the reason? Reason can be many. 3 reasons are listed here. Do poor people make pollution? Not correct. See, if suburb belong to poor people and it is having high pollution, so what is the reason? So one reason may be, do poor people make pollution? Not correct. Are polluted suburb only the place poor people can afford? Means they can, polluted suburb will be, cost will be less, right? The cost of houses will be less. So that's where poor people can afford to buy the house. Third reason is, there is a common link, such as factories. See, poor people means there is some place where there are a lot of factories. And around that, there will be a lot of workers. So that they will be the poor suburbs. So there will be a lot of factories with low paying jobs and a lot of pollution. So that's where a lot of poor people stay. So out of these Then guys, you have to go on mute. Somebody has to go on mute. You have to go on mute like Sarthak and Amit. Okay, guys. So what I meant to say, if X is increasing, that doesn't mean X is causing increase in Y. Understand? If X is increasing, Y is increasing, it doesn't mean that increase in X is causing increase in Y. There may be some other reason because of which both are increasing. Like poor people, poor suburbs are likely to have more pollution. So X is your poor suburb of the city, and Y is your high pollution. How they are related? So they can be related with. There can be many reasons. Poor people are not the cause of high pollution, right? Poor people are not the cause of high pollution. There may be many reasons because of which high pollution is there. So I meant to tell you only thing I want to tell you is, if X is increasing, Y is increasing. That doesn't mean that increase in X is causing increase in Y. Like here, you can say if rise in temperature, rise in ice cream sale. Both are, if rise in temperature is causing high sales of ice cream. So if rise in temperature is causing high sale of your ice cream sale. So that is, I can understand the causing. Temperature is rising, it is causing causing increase in sale for ice cream. I can understand. But here, my sunglass sale is increasing. Yes, sunglass sale is increasing, and then also ice cream scale is rising. So they are not correlated. I cannot relate sunglass with ice cream. Right? Sunglass and ice cream I cannot correlate. So sometime that means here X is not causing Y. Here X is causing Y. In this case, X is causing Y. Temperature is causing more ice cream to sell. But here, in case of sunglass and ice cream, sunglass sale is not causing ice cream sale. They are just like that related. It may be a coincidence, or there might be some other third factor to which both are related. Sunglass sale is rising, third factor to rise, and because of that ice cream sale is increasing. One more example I am giving you here is, I am giving you here is this example. Like poor suburbs are more likely to have high pollution. Poor suburbs are more likely to have high pollution. So there can be many reasons. Poor people are not causing high pollution. There may be many reasons which are listed here. So only thing means, if X is increasing, Y is increasing. If X increases, Y increases. That doesn't mean that X is causing increase in Y. It can be anything. Only thing we are seeing here is X is increasing, Y is also increasing. We cannot say that because of X, Y is increasing. That's it. Well, that's what you have to understand. That's it. Okay, so that's what you have to understand here. And see here. See the definition here. In statistics, correlation or dependence is a statistical relationship. Whether causal or not. Causal means increase in X may cause increase in Y, and it may not cause increase in Y. Causal or not, between two random variables or bivariate data. So your variable should be random, X and Y, and relationship between X and Y can be causal or may not be causal. X may cause increase in Y, X may not cause increase in Y. Okay, so like that. So with these things, we have learned three concepts today. Correlation, which belongs to a single variable. Covariance, which belongs to two variables, and it depends on scale or unit. Then correlation, correlation also between X and Y, two variables, but it is standardized version of covariance. It doesn't depend on It doesn't depend on scale of x can be anything, scale of y can be anything. If we vary both, still it will not vary. Correlation varies between -1 and 1. But covariance varies between -infinity to +infinity. Correlation and covariance varies between -infinity to +infinity, and variance is always a positive number, 0 to infinity. Like that, variance means 0 to infinity, covariance -infinity to +infinity, and correlation -1 to 1. So these things we have understood. And with this, I want to stop for today's lecture.